Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to do some exam review for our thermodynamics unit. Let's go ahead and get started with problem number 1. Problem number 1 says, which statement is false? A says, pressure is an intensive property. Intensive properties do not depend on the amount of substance present. They stay the same no matter how much material you have. Examples include temperature, pressure, and density. So pressure is intensive, meaning this statement is true. B says volume is an extensive property. Extensive properties do depend on the amount of material. So if you double the system, the volume doubles. So volume is a textbook example of an extensive property. That makes this statement true as well. C says work is a path function. A path function is a quantity that depends on the process or the path taken between two states, and not just the initial and final values. Both heat and work fall into this category. So work being a path function is true. Finally, D says heat is a state function. So this is where we find the false statement. Heat is not a state function. Like work, heat depends on the path taken to get from one state to another. A state function depends only on the initial and final states of the system, and not the process used to get there. Examples of state functions include internal energy, enthalpy, entropy, temperature, and volume. But heat, no, that is a path function. The amount of heat transferred varies depending on the path. Therefore, option D is false, and that is our correct answer for problem 1. Problem 2 says, which statement is true? We're given 3 statements here about types of systems in thermodynamics, and our job is to identify which ones correctly describe the behavior of matter and energy transfer. Let's start with statement 1. Statement 1 says, open systems allow transfer of matter and energy. This is true. In an open system, both energy and matter can flow freely between the system and its surroundings. So statement 1 is correct. Statement 2 says closed systems allow transfer of matter, but not energy. This is false. A closed system actually allows the transfer of energy, but not matter. So that means heat or work can enter or leave, but no physical substances can go in or out. Since this statement claims the opposite, that matter can transfer but energy cannot, it's incorrect. Finally, statement 3 says isolated systems don't allow transfer of matter or energy. This is true. In an isolated system, nothing gets in or out. No energy, no matter. That means the true statements are 1 and 3, and that makes the correct answer for problem 2, B. Problem 3 says a system releases 125 kilojoules of heat, while 104 kilojoules of work is done on it. What are the signs of heat, work, and change in internal energy, all referring to the system? Let's start with figuring out the assignment for heat, labeled as lowercase q. It states that the system releases heat. That means heat is leaving the system and entering the surroundings. In thermodynamics, when heat is leaving the system, we assign that a negative sign. So Q is going to be less than 0. Now let's look at work, labeled as lowercase w. The question says that work is done on the system. That means the surroundings are compressing or otherwise applying force to the system. When work is done on the system, energy is being transferred into the system, so this is considered positive work. That means that work is greater than 0. Now let's determine the sign of delta U, which is the change in internal energy. The first law of thermodynamics tells us that the change in internal energy of a system is equal to heat plus work. So delta U equals Q plus W. We can then begin to plug in the values with their signs and calculate delta U. Since the system is losing 125 kilojoules of heat, Q is negative 125 kilojoules. And since 104 kilojoules of work is being done on the system, W is positive 104 kilojoules. Now we add them together to get negative 21 kilojoules. That means that the internal energy of the system has decreased, so delta U is less than 0. So to summarize, heat is negative, work is positive, and change in internal energy is negative. That matches answer choice C. Let's tackle problem 4 now. Problem 4 says which statements are false. Let's work through each option carefully. A says delta S is positive when order increases. Delta S is the change in entropy, which is a measure of disorder in a system, or in other words, energy dispersal. A positive delta S means that the system is becoming more disordered, while a negative delta S indicates that the system is becoming more ordered. This statement says that entropy increases when order increases, but that's backwards. If order increases, that means things are becoming more organized, so entropy is decreasing. Therefore, this statement is false. In fact, 4 is A. But we're still going to work through B, C, and D. B says delta H is positive for an endothermic process. Delta H represents enthalpy, or the heat content of a system. In an endothermic process, the system absorbs heat from the surroundings. That means energy is entering the system, so the enthalpy increases. And a positive delta H indicates heat is flowing into the system. So this statement is true. C says delta G is negative for spontaneous processes. Delta G represents the Gibbs free energy change, and a negative value for delta G means that the process can occur spontaneously. That means it does not require energy input or continuous energy input to happen. That makes this statement true as well. Finally, D says that Q is positive when the system absorbs heat. Q represents heat, and by thermodynamic convention, heat is positive when it flows into the system. So if the system absorbs heat, Q is greater than 0, and that makes this statement true as well. So to summarize, statement A is the only false statement. 4 is A. Problem 5 says, fill in the blanks to make this a true statement. In a closed system, exothermic reactions at constant volume and temperature cause blank in delta U of the system and blank in delta U of the universe. First, we're told that the reaction is exothermic. That means that the system is releasing heat to the surroundings. And because energy is leaving the system, then the system's internal energy is going to be going down. So the change in internal energy of the system, or delta U of the system, is negative. That means there's a decrease in delta U of the system. That immediately helps us eliminate any answer choices that say that the system's energy is increasing. So we can cancel out A and B. Now, for the second part of the question, what happens to the internal energy of the universe? This is where we use the first law of thermodynamics, the law of energy conservation. It tells us that energy cannot be created or destroyed, only transferred. Mathematically, the change in energy of the universe is equal to the sum of the energy changes of the system and of the surroundings. So delta U of the universe equals delta U of the system plus delta U of the surroundings. Now, in a closed system, no matter is exchanged with the surroundings, but energy can be. So when the system loses heat, the surroundings gain that heat. That means that the decrease in energy of the system is exactly balanced by an equal increase in energy of the surroundings. So when you add those together, the negative change from the system and the equally positive change from the surroundings, you get zero net change in the energy of the universe. Therefore, delta U of the universe does not change. So putting it all together, delta U of the system decreases and delta U of the universe shows no change. That matches answer choice C. Now, problem 6 asks, which statement is false? Let's read A first. A says in an open system, pressure is constant. So Q is equal to Q sub P. This is true. In many lab settings, reactions are carried out in open containers, like a coffee cup, where pressure remains constant because the system is open to the atmosphere. Under constant pressure conditions, the heat exchanged with the surroundings is represented as Q sub P, and it reflects the enthalpy change. So this statement is true. B says, in a closed system, volume is constant. So Q equals Q sub V. This is also true. In a closed system, like a bomb calorimeter, the volume does not change. That means no pressure volume work is done, and the heat that's exchanged under these conditions is in fact labeled Q sub V, which reflects the change in internal energy. So again, this statement is true. C says, in a closed system, there is no pressure volume work. This is also true. Pressure volume work, or P delta V work, occurs when the volume of the system changes. But in a closed system where the volume is held constant, there's no change in volume, so no pressure volume work is performed. This statement is consistent with what we know, so it's true. Finally, D says delta U of the system is equal to heat at constant pressure. This is the false statement. The change in internal energy, delta U, is only equal to heat at constant volume, not constant pressure. That's because at constant pressure, some of the heat goes into doing pressure volume work, like expanding against atmospheric pressure. So the heat at constant pressure is actually equal to enthalpy change, not internal energy. At constant volume, though, there is no pressure volume work, so all of the heat contributes directly to changing internal energy. That's when delta U equals Q sub V, not Q sub P. So this statement is false, and that makes option D the correct answer to this question. Let's move on to our next problem. This problem says a system initially has an internal energy of 501 joules. It undergoes a process during which it releases 111 joules of heat to the surroundings and does work of 222 joules. What is the final energy of the system? Let's start by identifying what we're given. The initial internal energy is 501 joules. The system releases 111 joules of heat. That means heat is leaving the system, so Q is negative 111 joules. Then we're told that the system does 222 joules of work. That means energy is being used by the system on the surroundings, so W is also negative 222 joules. Now we use the first law of thermodynamics, which states that the change in internal energy is equal to heat plus work. Delta U equals Q plus W. So let's plug in the values. Delta U equals negative 111 joules plus negative 222 joules, which gives us a total change of negative 333 joules. So that is the value of delta U. Now we use this to then find the final internal energy. Remember that delta U equals final energy minus initial energy. So we write final energy minus 501 joules, which we're told is the initial energy. And that is going to be equal to negative 333 joules. To solve for U final then, we're going to add 501 joules to both sides, and that gets us that the final energy is equal to negative 333 plus 501 joules, and that is 168 joules. That matches answer choice B. Problem 9 says a system has 400 kilojoules of work performed on it by the surroundings with an internal energy change of negative 700 kilojoules. How much energy did the system gain or lose as heat? Once again, let's start by organizing what we know. The change in internal energy, delta U, is given as negative 700 kilojoules. That means that the system loses energy overall. Then we're told that the work done on the system is 400 kilojoules. Since the surroundings are doing work on the system, that's going to be positive work. So W is positive 400 kilojoules. Our goal is to find Q, the heat. We use the first law of thermodynamics, which says that delta U equals Q plus W. So we plug in our known values to begin. Negative 700 kilojoules equals Q plus 400 kilojoules. To solve for Q, we are going to subtract 400 kilojoules from both sides. This gets us that Q is equal to negative 700 minus 400, and that is equal to negative 1,100 kilojoules. So what does that mean? A negative value for Q means that the system lost heat. Specifically, the system lost 1,100 kilojoules of energy as heat. That matches answer choice C. Problem 10 says, a 1 gram piece of antimony is at 10 degrees Celsius and it's placed in an oven for 1 hour. At the end of the hour, it has a final temperature of 55 degrees Celsius. A 1-gram piece of cadmium, a 1-gram piece of copper, and a 1-gram piece of zinc were also placed in the oven. How many of the other metals will be hotter than antimony when removed from the oven? Let's break this down by understanding what determines temperature change when something is placed in a heat source like an oven. Here we're going to use the equation Q is equal to mc delta T, where Q is the heat absorbed, M is the mass, C is the specific heat capacity, and delta T is the temperature change. Now here's the key. All of the metals were placed in the same oven for the same amount of time, and they all have the same mass, 1 gram. That means that the amount of heat absorbed, Q, is effectively the same for all 4 metals. So since Q and M are constant, any difference in temperature change must come from differences in specific heat capacity. If we rearrange the equation to solve for temperature change, we get that delta T equals Q divided by mass times the specific heat capacity. And once again, since M and Q are the same for all metals, the metal with the lowest specific heat capacity will experience the largest temperature increase. So the higher the specific heat, the more heat it takes to raise the temperature, so those metals will have smaller temperature changes. Looking at the specific heat values we're given in the problem, we notice that antimony has the lowest specific heat capacity. It has a specific heat capacity of 0.21 joules per gram per Kelvin. That means it will undergo the greatest increase in temperature. The other metals all have higher specific heat capacities, so they're going to heat up more slowly and they're going to reach lower final temperatures. So the question asks, how many of the other metals will be hotter than antimony? And the answer is none. Antimony will be the hottest because it requires the least heat to reach a high temperature. That means that the correct answer is 0. Answer choice A. 11 says, a new polymer was developed that may be a good source of insulation in home building. As an initial test, an experiment was performed to determine the heat capacity of the new material. 4 grams of the material was heated to 50 degrees Celsius and then added to a coffee cup calorimeter containing 50 grams of water at 24 degrees Celsius. The temperature of the water rose to 25 degrees Celsius. Assuming no heat loss to the calorimeter, what is the heat capacity of this new substance? And here we're given the specific heat capacity for water. When 2 substances come into thermal contact, the heat lost by the hotter substance is equal in magnitude and opposite in sign to the heat gained by the cooler one. So we can write heat lost by the polymer equals negative heat gained by the water, or Q of polymer equals negative Q of water. Now let's write out both expressions using the equation Q equals mc delta T, where m is the mass, C is the specific heat capacity, and delta T is the change in temperature. So we write that the mass of the polymer times the specific heat capacity of the polymer times the change in temperature of the polymer equals negative multiplied by the mass of water times the specific heat capacity of the water times the temperature change of the water. With this in place, let's plug in what we know on the polymer side first. We know we have 4 grams of our polymer. We don't know any information on the specific heat capacity of the polymer. That is our goal for the problem. What we do know, though, is the initial and final temperature of the polymer. The final temperature is 25 degrees Celsius, and the initial temperature is 50. So delta T here is going to be 25 minus 50, or negative 25 degrees Celsius. On the water side, we know we have 50 grams of water. The specific heat capacity of water is 4 joules per gram per degree Celsius. And the temperature change is 25 degrees Celsius minus 24, or plus 1 degree Celsius. Simplifying things gets us that 4 grams times the specific heat capacity of the polymer times negative 25 degrees Celsius equals negative 50 multiplied by 4 multiplied by 1, which is equal to negative 200 joules. Then if we multiply out the polymer side, 4 times negative 25 is equal to negative 100 grams times Celsius. So what we've reached here on this equation is that the specific heat capacity of the polymer multiplied by negative 100 grams times Celsius is equal to negative 200 joules. Our final step to solve for CP is to divide both sides by negative 100 grams times degrees Celsius. And that gets us that the specific heat capacity of the polymer is 2 joules per gram per degree Celsius, which matches answer choice B. Problem 12 says, what is the value of work when a container volume increases from 2 liters to 4 liters with a pressure of 100 kilopascals? Let's start by writing down the formula for pressure volume work. Work equals negative pressure times change in volume. From the question, we know that pressure is equal to 100 kilopascals, and we know that the change in volume delta V is the final volume minus the initial volume. That's 4 liters minus 2 liters, which gives us a change of positive 2 liters. Then we plug this into the formula to get that work is equal to negative 100 kilopascals times 2 liters. And that is equal to negative 200 liters times kilopascals. Next, we use the unit conversion. Since 1 liter times kilopascal equals 1 joule, this becomes negative 200 joules. Finally, let's interpret the sign. Since the volume is increasing, the system is expanding. And when a system expands, it does work on the surroundings. That means energy is leaving the system in the form of work, which is why the sign is negative. So the final answer is negative 200 joules, and this is work done by the system. That matches answer choice D. Problem 13 says, which of the following statements is false? Let's cover each option. A says enthalpy change for a reaction is heat lost or absorbed at constant pressure. This is true. One of the defining features of enthalpy is that under constant pressure, the change in enthalpy, delta H, is equal to the heat transferred, Q sub P. So delta H equals Q at constant pressure. This is the basis for constant pressure calorimetry, and it's why enthalpy is used to track heat changes in a reaction. So this statement is correct. B says enthalpy is equal to the internal energy at constant pressure and volume. Enthalpy is defined as delta H is equal to delta U plus P delta V. U is internal energy, P is pressure, V is volume. Now, if both pressure and volume are constant, then P delta V is 0, and the change in enthalpy equals the change in internal energy. So at constant pressure and constant volume, delta H equals delta U, and this statement is true. C says large changes in volume cause larger differences between delta H and delta U. This is also true. So from the enthalpy equation, delta H is equal to delta U plus P delta V. This tells us that when volume changes significantly, the P delta V term becomes large, meaning delta H and delta U diverge. And this is especially noticeable in reactions involving gases where large expansions or compressions happen. So this statement is true. Finally, D says enthalpy changes only occur when temperatures change. This is the false statement. Enthalpy changes, they can also occur without a temperature change, most notably during phase changes. For example, when ice melts at 0 degrees Celsius, the temperature stays constant until the entire sample has melted. Yet heat is still being absorbed, and that heat corresponds to a change in enthalpy, specifically the enthalpy of fusion for our example. So enthalpy can change even if temperature does not change. This makes option D false, and therefore the correct answer to this question. The next problem says the melting point of methanol is negative 98 degrees Celsius, and the boiling point is 65 degrees Celsius. What information is required to determine the amount of heat needed to increase the temperature of 10 grams of methanol from 40 degrees Celsius to 98 degrees Celsius? Let's visualize this on a heating curve. We're starting at 40 degrees Celsius, which is in the liquid phase because it's above the melting point and below the boiling point. And then we're ending at 98 degrees Celsius, which is in the gas phase since it's above the boiling point. So as we heat the methanol from 40 to 98 degrees, we're going through 3 steps. The first step, we are warming the liquid from 40 to 65 degrees. Then in the second step, we're vaporizing the liquid at 65 degrees. And finally, we warm up the vapor from 65 to 98 degrees. Let's now walk through what's needed for each of those steps. For the first step, where we are warming the liquid, we're going to need the specific heat capacity of liquid methanol, which we're going to call C liquid. For the second step, the phase change from liquid to gas, we're going to need the enthalpy of vaporization, delta H vaporization. And then for the third step, where we are heating the gas, we're going to need the specific heat capacity of methanol in the gas phase, or C gas. So the 3 values we need are C gas, C liquid, and delta H vaporization. That makes the correct answer choice B. Problem 15 says, calculate the total heat required to convert 2 moles of ammonia from negative 35 degrees Celsius to negative 23 degrees Celsius. The following data for ammonia may be useful. We're given the specific heat capacity of the liquid phase and the gas phase. We're given the boiling and melting point, and we're also given delta H of vaporization. Let's start by figuring out what changes are happening. We're starting at negative 35 degrees Celsius, which is below the boiling point. So ammonia starts off in the liquid phase. Then we're ending at negative 23 degrees, which is above the boiling point. So ammonia ends as a gas. That means we're passing through 3 key steps. First, we're warming the liquid from negative 35 to negative 33 degrees. Then we are vaporizing the liquid at negative 33 degrees Celsius. And finally, we're warming the liquid up from negative 33 to negative 23 degrees Celsius. Let's calculate the heat required for each step. Step 1 is heating the liquid ammonia, starting from negative 35 degrees Celsius to negative 33 degrees Celsius. To calculate the amount of heat absorbed during this temperature change, we can use a familiar equation from thermochemistry, and that equation is Q equals mc liquid delta T, where Q is the heat absorbed, M is the mass in grams, C is the specific heat in joules per gram per degree Celsius, and delta T is the temperature change. But in this problem, you've noticed that we're given the amount in moles, not grams, and the heat capacity is expressed in joules per mole per degree, not per gram. So instead of using mass, we can use moles and apply the molar form of the equation. So Q equals the number of moles, N, multiplied by the molar specific heat capacity, multiplied by delta T. So we're using the molar form of the equation because the data is already given in moles and molar heat capacity, and that saves us from converting to grams and using the molar mass. So this is the form of the equation. Let's plug in the values. N is equal to 2 moles. The specific molar heat capacity for liquid ammonia is equal to 80 joules per mole per Kelvin. So we plug that in. Now, we've discussed in previous lectures how Celsius and Kelvin for delta T, you can use either or. They're going to equal the same when you take the difference because 1 unit in Kelvin is equal to 1 unit in Celsius. So technically, we can rewrite 80 joules per mole per Kelvin to 80 joules per mole per Celsius, and then take delta T in Celsius. We can take that difference, delta T, in Celsius. And that way the units cancel out, so we get our final answer in joules. The temperature change for this first part is going from negative 35 degrees Celsius to negative 33 degrees Celsius, which is a 2-degree increase. So for this first step, Q is equal to 2 multiplied by 80 multiplied by 2, which is equal to 320 joules or 0.320 kilojoules. Step 2 is the vaporization step, where ammonia is changing from liquid to gas at its boiling point, which is negative 33 degrees Celsius. During a phase change, the temperature stays constant, but energy is still absorbed or released. That energy goes into breaking intermolecular forces, not raising the temperature. So we're no longer going to use Q equals mc delta T because delta T is 0 during a phase change. Instead, we use a different form of the heat equation that's specific to phase changes. If we're given mass, we can use Q equals m multiplied by delta H vaporization, where delta H vaporization is the enthalpy of vaporization in joules per gram, and M is the mass in grams. But again, in this problem, we're working with moles, and we're given the enthalpy of vaporization as 24 kilojoules per mole. So we can use the molar form of this equation, Q equals N multiplied by delta H vaporization in its molar form. Now we can plug in the values we know. N is 2 moles. and delta H vape is 24 kilojoules per mole. Notice moles cancel out. We're going to get our final answer in units of kilojoules. 2 times 24 is equal to 48. Then finally, step 3 is heating the ammonia gas from its boiling point of negative 33 degrees Celsius up to negative 23 degrees Celsius after it has fully vaporized. Since this is another temperature change and not a phase change, we can go back to using the heat equation for warming. Again, since we're working in moles and the heat capacity is given as molar heat capacity, we will use Q is equal to N multiplied by the molar heat capacity multiplied by delta T. We have all these values, so we can plug them in. We have 2 moles. This is multiplied by the molar heat capacity of the gas, which is 37 joules per mole per Kelvin, equal to 37 joules per mole per Celsius. So we can write it in that form since our temperature is in Celsius. And then delta T is final temperature minus initial temperature. So negative 23 minus negative 33 degrees Celsius. When we plug this into a calculator, we're going to get approximately 740 joules or 0.740 kilojoules. Finally, we can add all of these values together. 0.320 plus 48 plus 0.740 to get the final and total heat required, which is going to be approximately 49.06 kilojoules. So the answer to problem 15 is C. Problem 16 says, how much heat does it take for 78.11 gram sample of benzene to go from 269 Kelvin to a liquid at 279 Kelvin? The following physical data for benzene may be useful. We're given the molar specific heat capacity for the liquid, solid, and gas phase. We're given delta H of vaporization and delta H of fusion. We're also given the molecular weight, the boiling point, and the melting point. Let's begin by identifying what phase changes or temperature changes are taking place. We're starting at 269 Kelvin, which is below the melting point of benzene. And then we end right at 279, which is exactly at the melting point. That means we begin with solid benzene and then we end with liquid benzene right at the melting point. So we're going through 2 segments of the heating curve. We're warming the solid from 269 to 279 Kelvin, and then we're melting the solid at 279 Kelvin. Let's calculate the heat required for each step. Step 1 involves heating the solid benzene. This is a temperature change, so we use the heat equation. Because the heat capacities are given per mole, we are going to take our given mass of benzene and the given molecular weight, and we're going to convert that to moles so we can use the molar form of the equation. Q is equal to N multiplied by the specific molar heat capacity multiplied by delta T. That is going to be more convenient here. So we're told we have a sample with a mass 78.11 grams for benzene. And then benzene's molar mass is also 78.11 grams per mole. So that's exactly 1 mole of benzene. Let's begin to plug things into our first equation. We have 1 mole. This is multiplied by the specific molar heat capacity of solid benzene, which is 118 joules per mole per Kelvin. And then we do the temperature difference. Final temperature minus initial temperature, 279 minus 269. When we multiply this out, we get 1,180 joules or 1.18 kilojoules. Now we move on to the second step. The second step involves melting benzene. This is a phase change, so we do not use delta T. Instead, we use the enthalpy of fusion. So Q is going to be equal to the number of moles multiplied by the change in enthalpy of fusion in its molar form. So this will be 1 mole multiplied by 10 kilojoules per mole. That gives us 10 kilojoules. Now we add both contributions, 1.18 kilojoules to warm the solid and 10 kilojoules to melt it. That gives us a total of 11.18 kilojoules. So the correct answer is choice C. Moving on to problem 17. Problem 17 says reactants in a chemical reaction have an internal energy of 400 kilojoules and the products have an internal energy of 200 kilojoules. What is the change in internal energy? To calculate the change in internal energy, we use the definition that delta U equals U final minus U initial. That means U final is the internal energy of the products, which is 200 kilojoules, and U initial is the internal energy of the reactants, which is 400 kilojoules. So we plug in delta U is equal to 200 minus 400 kilojoules, and that is equal to negative 200 kilojoules. A negative change in internal energy means that energy was released by the system. When energy is released, we call the process exothermic. So the change in internal energy is negative 200 kilojoules, and the reaction is exothermic. That makes the correct answer for problem 17, B. Problem 18 says, identify which statement is false about the components of a bomb calorimeter. A bomb calorimeter is a device that's used to measure the heat released during combustion reactions under constant volume conditions. To function properly, it includes several essential components, each with a very specific role that's important in ensuring accurate energy measurements. So let's work through each option. A says a spark is required to ignite the reaction. This is true. A bomb calorimeter contains a small ignition system, typically a wire or fuse, that provides a spark to initiate combustion of the sample that's inside the sealed chamber. This is a core component of the calorimeter setup. It's a true statement. B says a thermometer is required to measure the reaction temperature. This statement is incorrect, not because a thermometer isn't used, but because it misidentifies what is being measured. In a bomb calorimeter, we're not measuring the temperature of the reaction itself. Instead, we measure the temperature change of the surrounding water in the calorimeter. The heat from the combustion reaction is transferred to this water, and it's the water's temperature change that tells us how much heat was released. So the idea is close, but the phrasing is inaccurate. In fact, 18 is B, but we'll still work through C and D. C says a stirrer to ensure the change in temperature is accurately measured. This is true. A stirrer is included to keep the water well mixed so that heat is evenly distributed. Without it, you might get hot spots or temperature gradients, which would distort the temperature reading. Finally, D says thick insulated walls prevent the transfer of energy. This is also correct. The calorimeter is designed to be as thermally isolated as possible so that all of the heat released by the reaction stays in the system. If heat escaped to the environment, then the results would be inaccurate. Therefore, the answer for this problem is B. Let's move on to problem 19. Problem 19 says when 22 grams of graphite, which is solid carbon, is completely combusted in a bomb calorimeter containing 100 grams of water, a temperature increase of 10 degrees Celsius is observed. The heat capacity of the calorimeter is 4 kilojoules per degree Celsius, and the specific heat capacity of the water is 4 joules per gram per degree Celsius. Calculate the heat involved, including correct sign, when 6 grams of graphite is combusted. This is a bomb calorimeter, which means we're measuring the heat released by the combustion reaction indirectly by tracking how much heat was absorbed by the surroundings. In this case, the surroundings include both the water and the calorimeter. Since energy is conserved, the heat that's released by the reaction equals the negative of the heat absorbed by the surroundings. So we can say the heat of the system equals negative heat of the surroundings. To find how much heat the surroundings absorbed, we need to calculate the heat absorbed by both the water and the heat absorbed by the calorimeter and add those together. For the water, we use the equation mass times specific heat times the change in temperature. The mass of the water is 100 grams. The specific heat is 4 joules per gram per degree, and the temperature change is 10 degrees. So we multiply this out, and it gives us 4,000 joules. But we want our answer in kilojoules. We know this just by looking at the answer choices. All our answer choices are in units of kilojoules. So we're going to convert 4,000 joules to kilojoules. That's equal to 4. Now it's time for us to consider the contribution from the calorimeter. It's treated as a single object with a heat capacity of 4 kilojoules per degree. And since the temperature went up by 10 degrees, we multiply 4 kilojoules per degree Celsius by 10 degrees Celsius to get 40 kilojoules. Now we're going to add both parts together. Adding both parts together, the surroundings absorbed 4 kilojoules from the water and 40 kilojoules from the calorimeter for a total of 44 kilojoules. Since this energy was absorbed by the surroundings, it must have been released by the system. That's why we apply a negative sign. So the total heat released by the combustion of 22 grams of graphite is negative 44 kilojoules. But we're not done yet. The question asks how much energy is released when only 6 grams of graphite is combusted. So we scale the heat accordingly. We take the value of negative 44 kilojoules. We're going to divide it by 22 grams. This is going to give us the amount of heat per gram. And then we'll multiply that by 6 grams. So this is going to give us negative 12 kilojoules. The correct answer is A. Problem 20 says, determine delta H for the combustion of methane given the following balanced equation. 1 mole of methane reacts with 2 moles of oxygen gas to give us carbon dioxide, 1 mole of that, and 2 moles of water. To find the enthalpy change for the combustion of methane, we can use bond enthalpies, which tell us how much energy is required to break specific chemical bonds. The key formula is that the enthalpy change for a reaction equals the total energy required to break all of the bonds in the reactants minus the total energy released when new bonds are formed in the products. So in other words, delta H equals bonds broken minus bonds formed. Let's look at the balanced equation for the combustion of methane. In our reactants, we have a methane molecule. In the methane molecule, we have 4 carbon-hydrogen bonds. We know for each carbon-hydrogen bond broken, that is going to require 413 kilojoules per mole of energy. We get this from the table that was on the first page when we started this problem set. So for a methane molecule, we're going to break 4 carbon-hydrogen single bonds. To get the full amount that is, we're going to multiply 4 times 413, and that gives us 1,652 kilojoules per mole. Then we consider the oxygen molecules in the reactants as well. Each oxygen molecule has a double bond between the 2 oxygen atoms. Since there are 2 oxygen molecules, that's 2 double bonds. The bond energy for each oxygen-oxygen double bond is 498 kilojoules per mole, and when we multiply that by 2, we get 996 kilojoules per mole. Adding both parts together, the total energy needed to break the bonds in the reactants is 1,652 plus 996, which equals 2,648 kilojoules. Now we calculate the energy released when new bonds are formed in the products. So in the products, we have carbon dioxide. In carbon dioxide, the carbon forms 2 double bonds with 2 oxygen atoms. Each carbon-oxygen double bond releases 799 kilojoules per mole. Since we have 2 of them, we multiply 2 times 799, which gives us 1,598 kilojoules. Now we have water. That's our last and final product for us to consider. For each water molecule, we have 2 oxygen-hydrogen bonds. Since we have a total of 2 water molecules, that means there are a total of 4 oxygen-hydrogen bonds. Each oxygen-hydrogen bond needs 467 kilojoules per mole. That's the amount that's released. So 4 times 467 gets us 1,868 kilojoules per mole. When we add those together, the total energy released by forming product bonds is 1,598 plus 1,868, which is 3,466 kilojoules per mole. Now we go back to our equation. The enthalpy change is equal to the energy used to break bonds, which is 2,648 kilojoules, minus the energy released when forming bonds, 3,466 kilojoules. So delta H is going to be equal to negative 818 kilojoules per mole. Since this value is negative, that tells us that the reaction is exothermic. It releases energy. The correct answer is D. Problem 21 says, using bond energies, and that the delta H of the reaction is equal to negative 249 kilojoules per mole, calculate the nitrogen-fluorine bond energy. To find the nitrogen-fluorine bond energy, we're going to use the enthalpy change for the reaction along with the bond energies for the other bonds involved. The formula we use here is that the enthalpy change of the reaction equals the total bond energy of the bonds broken minus the total bond energy of bonds formed. We're given that the enthalpy change for the reaction is negative 249 kilojoules per mole. That means that the reaction is exothermic. It releases energy overall. Now let's start by identifying the bonds that are broken. On the reactant side, we have 1 mole of nitrogen gas and 3 moles of fluorine gas. The nitrogen molecule contains 1 nitrogen triple bonded to another nitrogen, and each fluorine molecule contains a single fluorine-fluorine bond. So the bonds broken are 1 nitrogen triple bond and 3 fluorine-fluorine bonds. This is going to be equal to the bond energy for the nitrogen triple bond, which is 945 kilojoules per mole, and the bond energy for 3 fluorine-fluorine single bonds. That is going to be 159 kilojoule per mole for each one. We multiply that by 3. Then we take the difference between the sum of those values and the energy required to form 2 moles of NF3. Nitrogen is single bonded to 3 fluorines, and since we have 2 moles of that, that's a total of 6 nitrogen-fluorine bonds. So we add this into our equation. Since the bond energy for nitrogen-fluorine is what we're looking for, we're going to call that value X. So now we have 945 kilojoules per mole plus 3 times 159 kilojoules per mole. We take the sum of that. That sum is then subtracted by 6x. X is what we're trying to figure out. And we know that the total delta H of the reaction is negative 249 kilojoules per mole. Negative 249 kilojoules per mole is equal to 1,422 kilojoules per mole minus 6x. Then we subtract 1,422 from both sides, and then we divide both sides by 6 to get X. X is the bond energy of a single nitrogen-fluorine bond. That is equal to 279 kilojoules per mole. So problem 21 is B. Problem 22 says, calculate delta H of the reaction for the following reaction using the bond energies on the front page. The structure of N2 is that it is a nitrogen-nitrogen triple bond, and there are only single bonds between the nitrogen and hydrogen atoms in ammonia. Once again, the enthalpy of the reaction equals the sum of the bond energies of bonds broken minus the sum of the bond energies of the bonds formed. That's because energy must be added to break bonds, and energy is released when new bonds are formed. In this case, we're given a balanced reaction. 1 molecule or 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to form 2 moles of ammonia. The structure of nitrogen gas is a nitrogen-nitrogen triple bond, and each hydrogen molecule is made up of a hydrogen-hydrogen single bond. Finally, we have ammonia. Ammonia has 3 nitrogen-hydrogen single bonds per mole, and since there are 2 moles in the products for ammonia, that's a total of 6 nitrogen-hydrogen bonds that are formed. Now we calculate the total energy required to break the bonds in the reactants. Breaking a nitrogen-nitrogen triple bond takes 945 kilojoules per mole. Breaking the 3 hydrogen-hydrogen single bonds takes 3 times 432 kilojoules per mole. That gives us 1,296 kilojoules per mole. Adding those together, the total energy input to break the bonds is 945 plus 1,296, which equals 2,241 kilojoules per mole. Next, we calculate the energy released when new bonds are formed. Each nitrogen-hydrogen single bond releases 391 kilojoules per mole when formed, and since we form 6 of them, we multiply 6 by 391 to get 2,346 kilojoules per mole. Now we apply the formula. Delta H for this reaction equals 2,241 minus 2,346, and that difference is equal to negative 105 kilojoules per mole. So the enthalpy change for the reaction is negative 105 kilojoules per mole, which means that the reaction is exothermic, And the correct answer is B. Problem 23 says, which chemical equations correctly represent the heat of formation? The heat of formation refers to the enthalpy change when exactly 1 mole of a compound is formed from its elements in their standard states under standard conditions. That means that the equation must be balanced, that the products must be a single compound, and the reactants must be the elements in their most stable form. Looking at equation 1, we see 2 moles of lithium solid react with 1 mole of oxygen gas to form lithium oxide. But the product here is lithium, Li2O. Oxygen is not balanced here. 1 mole of oxygen gas provides 2 oxygen atoms, but in the product, we only see 1 oxygen atom. This means that the equation doesn't accurately reflect the formation of 1 mole of product from elements in their standard states with the correct stoichiometry. So equation 1 is incorrect. Now looking at equation 2, we have 2 carbon atoms in the graphite form, which is the standard state of carbon, and 2 hydrogen gas molecules. This is also the standard state of hydrogen. These react to form 1 mole of ethylene gas, C2H4. This reaction is correctly balanced and it starts with the appropriate standard elements. We are forming exactly 1 mole of the compound and all the reactants are in their standard states. So this equation meets all of the criteria for a formation reaction and it's correct. Now for equation 3, we have sodium solid reacting with oxygen O and 1/2 of hydrogen gas, 1/2 mole of hydrogen gas. The product is sodium hydroxide. The issue here is that oxygen is not in its standard state. Oxygen in its standard state is O2 gas, not atomic oxygen. So this disqualifies equation 3 as a proper formation equation because it doesn't start from the elements in their standard state. So 3 is incorrect. Therefore, the only equation that correctly represents the heat of formation is equation 2, and 23 is answer choice B. Let's move on to problem 24. Here we want to determine delta H of the reaction for the following chemical equation. To calculate the enthalpy change for the reaction, we're going to use the standard equation for the enthalpy of reaction that is based on the standard enthalpies of formation. This equation tells us that the enthalpy change of the reaction equals the sum of the changes in standard enthalpy of formation of the products, each multiplied by its stoichiometric coefficient, minus the sum of the changes in standard enthalpy of formation of the reactants, also each multiplied by its coefficient from the balanced chemical equation. So in this equation, the variable n represents the number of moles of each substance. Let's begin by identifying the values we need. The balanced chemical reaction is 1 mole of silane gas reacts with 2 moles of diatomic oxygen gas to form 1 mole of solid silicon dioxide and 2 moles of liquid water. From the table provided, we can look up the standard enthalpy of formation for each of these compounds. We'll start with the products. We have 2 different products, liquid water and silicon dioxide. The standard enthalpy of formation for liquid water is negative 285.8 kilojoules per mole. Since we have 2 moles of water forming, we multiply that by 2, and that gives us negative 571.6 kilojoules per mole. Now for solid Silicon dioxide, the standard enthalpy of formation is negative 910 kilojoules per mole, and we're only forming 1 mole, so we just take that value as is. Now we'll add the two product contributions together to get negative 1,481.6 kilojoules per mole. Now we turn to the reactants. First, we consider diatomic oxygen gas. Since oxygen is an element in its standard state, its standard enthalpy of formation is going to be defined to be 0. So we do not include it in our enthalpy sum. The only other reactant is silane gas, SiH4, for which the standard enthalpy of formation is equal to 34 kilojoules per mole. And since we have just 1 mole, the total enthalpy contribution from the reactants is just 34 kilojoules per mole. Now we apply the reaction enthalpy formula. The enthalpy change of the reaction equals the total enthalpy from the products, which is negative 1,481.6, minus the total enthalpy from the reactants, which is 34. And when we calculate this, we get negative 1,515.6 kilojoules per mole. The answer for problem 24 is A. Problem 25 says, determine the standard enthalpy of formation for sulfur trioxide given this information. Here again, we're going to use the standard equation for reaction enthalpy based on heats of formation. The balanced chemical equation, it tells us that 2 moles of silicon dioxide gas react with 1 mole of oxygen gas to form 2 moles of sulfur trioxide gas. The overall enthalpy change for the whole reaction is positive 1,030 kilojoules. We're also given that the change in standard enthalpy of formation for silicon dioxide gas is negative 911 kilojoules per mole, and our goal is to find the change in standard enthalpy of formation for sulfur trioxide gas. So we start with the reactants. We have 1 mole of oxygen gas, which is in its elemental form, meaning its change in standard enthalpy of formation is actually 0. We also have 2 moles of silicon dioxide gas, and we know that the enthalpy of formation for that is equal to negative 911 kilojoules. So we multiply 2 times that to get negative 1,822 kilojoules per mole. That gives us the total contribution from the reactants. Now we can plug things into the formula. The reaction enthalpy is 1,030 kilojoules per mole. On the product side, we have 2 moles of sulfur trioxide gas, and we're trying to calculate the change in standard enthalpy of formation for that. So we write 1,030 equals 2 times the change in standard enthalpy of formation for sulfur trioxide gas minus negative 1,822 kilojoules. These 2 negatives multiply out to give us a positive. From here, we're going to subtract 1,822 from both sides. That gets us that negative 792 kilojoules per mole is equal to 2 times the change in standard enthalpy of formation for sulfur trioxide gas. Finally, we're going to divide both sides by 2 to get our final answer. Here we get that the change in standard enthalpy of formation for sulfur trioxide gas is negative 396 kilojoules per mole, which corresponds to answer choice A. Let's move on to the next problem. Problem 26 says, calculate the enthalpy change for the formation of sulfur trioxide gas from its constituent elements in their standard states. The standard state of sulfur is solid sulfur, and for oxygen, it's oxygen gas. For this problem, we're going to apply Hess's law. Hess's law tells us that if a reaction can be expressed as the sum of 2 or more steps, then the overall enthalpy change is just the sum of the enthalpy changes for each individual step. So for the reactions we're given, we can manipulate them in a way where their sum gives us our target reaction. Whenever we flip a reaction, we have to make sure that the delta H sign is also flipped. And if we multiply a reaction by a coefficient, we also have to multiply delta H by that same coefficient. So keeping that in mind, we're told that the standard state of sulfur is solid sulfur, and the standard state of oxygen is diatomic oxygen gas. And the formation reaction we're interested in is 1 mole of solid sulfur plus 3/2 moles of oxygen gas give us 1 mole of sulfur trioxide gas. Then we're given these two reactions to work with. And alongside these two reactions, we have their associated enthalpy changes. The first reaction tells us that 1 mole of solid sulfur reacts with 1 mole of diatomic oxygen to form 1 mole of sulfur dioxide gas. And the enthalpy change for this reaction is negative 296.8 kilojoules per mole. The second reaction tells us that 1 mole of sulfur trioxide gas breaks down into 1 mole of sulfur dioxide gas and 1/2 mole of diatomic oxygen gas. The enthalpy change for this is positive 98.9 kilojoules per mole. Since our goal is to form sulfur trioxide gas as a product, we're going to need to reverse the second reaction. So we keep the first reaction as is, but we reverse this second reaction. And when we do that, we need to change the sign for delta H. For the initial reaction, it was positive 98.9 kilojoules per mole. Since we reversed the reaction, it is now negative 98.9 kilojoules per mole. Now we can add both reactions together. Notice that anything that appears in the same form and same quantity on the reactant and on the product side, those essentially cancel out. So when we look at these two reactions that we want to add together, we notice that for one reaction, sulfur dioxide appears as a product, and for the other reaction, it appears as a reactant. They essentially cancel each other out. So then we bring down everything else. We have solid sulfur. We have 1 mole of oxygen gas plus 1/2 mole of oxygen gas. That gives us 3/2 moles of oxygen gas. And that forms sulfur trioxide gas. So we got our target reaction. To get the associated delta H value, we simply have to add the delta H reactions for each individual reaction type here. And so this is just going to be negative 296.8 plus negative 98.9 kilojoules per mole. That gets us negative 395.7 kilojoules per mole. So the correct answer for problem 26 is A. Problem 27 says, calculate the enthalpy change for the following reaction. In the products, we have nitrogen dioxide. Nitrogen dioxide only appears in reaction 1 as a product as well, and they're both 1 mole. So we're going to keep reaction 1 as is for now, just looking at our product. Now let's take our focus to the reactants. In the reactants, we have nitric oxide gas. This also only appears in reaction 1 as a reactant as 1 mole as well. So this confirms that we should keep reaction 1 as is. Then our second reactant is 1 mole of atomic oxygen. The only reaction where atomic oxygen appears is reaction 3, but it appears as 2 moles and as a product. So what we're going to do here is we're going to flip the reaction and then divide by 2. That gets us that 1 mole of atomic oxygen decomposes into 1/2 mole of diatomic oxygen gas. And since we flipped and multiplied by 1/2, we need to do the same thing for delta H here. We flip the sign and we divide by 2. That gets us that delta H is equal to negative 247.5 kilojoules. Now, something else you'll notice is that ozone appears in these three reactions we're given, but it's not in our target reaction, which means we need to ensure that when we sum up these reactions, ozone cancels out, as well as diatomic oxygen gas, which is not in our target reaction. Looking at ozone first, it appears as a reactant, 1 mole, in reaction 1. And then it appears as a reactant as well in reaction 2. To ensure it cancels out, I'm going to go ahead and reverse reaction 2. So now ozone is a product. That means we flip the sign for delta H from negative to positive. In this manner, when we add these reactions up, ozone is going to cancel out because it appears as 1 mole in the reactants and 1 mole in the products. What about diatomic oxygen? Does that cancel out in the way that we've written these three reactions? We have a total of 3 divided by 2 moles of diatomic oxygen on the product side and the same on the reactant side. So in fact, they will cancel out. That means ozone cancels out and diatomic oxygen also does. And when we sum up these three reactions, what we're left with is 1 mole of nitric oxide gas, 1 mole of atomic oxygen, and that forms 1 mole of nitrogen dioxide gas. That's exactly what we want. Since we were able to accomplish that, to get delta H, we simply have to sum up these values right here, and that will get us negative 304.1 kilojoules, which means the correct answer for problem 27 is B. Let's move on to problem 28. Problem 28 wants us to identify the true statements. Let's work through each of these statements. Statement 1 says entropy increases as the number of microstates increase. This statement is true. In thermodynamics, entropy is a measure of disorder or the number of possible ways a system can be arranged at the microscopic level. The more microstates a system has, the more ways its particles can be arranged, and therefore the higher the entropy. This relationship is captured by the equation delta S is equal to K natural log W. Delta S is the change in entropy, K is the Boltzmann constant, and W is the number of microstates. So statement 1 is correct. Statement 2 says water freezing is a positive change in entropy. This statement is false. When water freezes, it goes from the liquid phase to the solid phase. Liquids have more molecular disorder than solids, so when water becomes ice, the particles become more ordered, not less. This means that the number of microstates actually decreases, and therefore entropy decreases. So freezing results in a negative entropy change, not a positive one. This statement is false. Statement 3 says the change in entropy for the universe is always 0. This statement is also false. According to the second law of thermodynamics, for any spontaneous process, the entropy of the universe increases. While it's true that entropy might decrease in a localized system, the total entropy change, including the surroundings, must be greater than 0 for spontaneous processes. So the entropy change of the universe is not always 0. In fact, for any natural spontaneous process, it's always positive. So only statement 1 is true, which means that the correct answer is A. The next problem says, rank the following from highest to lowest absolute molar entropy. To rank substances by their absolute molar entropy for this problem, we need to consider 2 key factors we discussed in lecture, and that's physical state and molecular complexity or molar mass. First, let's talk about physical state. Entropy increases with molecular freedom. So gases have the highest entropy, followed by liquids, and then solids, which have the least molecular motion, and hence the lowest entropy. Second, if we're comparing substances in the same phase, like two gases, we then look at molecular complexity or molar mass. Larger or more complex molecules generally have higher entropy because they have more ways to vibrate, rotate, and move. Now let's evaluate the compounds that are given in this question. We're comparing CH3, CH2OH. This is ethanol gas. This is a complex molecule. It's in the gas phase. All right, so it should have a very high entropy. This is in comparison to carbon dioxide, also in its gas phase. It's smaller though, and it's more simple of a molecule than ethanol, so keep that in mind. Finally, we compare that to solid carbon dioxide or dry ice. So as a solid, it's going to have the lowest entropy among the three. So if we put this together, carbon dioxide in its solid form is going to have the lowest entropy. Next is going to be carbon dioxide as a gas. It's still a gas, but it's more simple than ethanol. Ethanol has the highest entropy because it's a gas and it's the largest, most complex molecule of the three. So the answer that is correct is A. First, we have ethanol with the highest, then gaseous carbon dioxide, then solid carbon dioxide. Let's move on to problem 30. Problem 30 says which compound has the highest expected molar entropy? To determine which compound has the highest expected molar entropy, we're going to need to focus on molecular structure and flexibility, since all of the compounds listed here are in the same phase, and they actually have the same molecular formula, C4H8O, which means they all have the same molar mass. So differences in entropy here will be based on how rigid or flexible their structures are. More specifically, entropy increases with molecular motion and freedom of rotation. So we want to look for the quote-unquote floppiest structure, the one with the least amount of strain or rigidity. Molecules that are more linear or extended have more accessible rotational and vibrational states, which means higher entropy. On the other hand, structures with rings or double bonds in conjugation or branching are going to restrict motion, so they will generally have lower entropy. Let's look first at butanoate. So this is a straight chain ketone. It's fairly linear and it has some flexibility, but it has this double bond to an oxygen that's kind of branching out, which slightly reduces rotational freedom around the carbonyl. Then our next molecule is epoxybutane. What we notice here is that the molecule contains a three-membered ring, and ring structures are very rigid. The ring is going to restrict both bond angles and torsional motion, so that's going to reduce entropy significantly. In fact, between the two, butanoate is going to have higher molar entropy. Then we can look at our third structure. This molecule is linear, no branching, but it also has this terminal double bond. Now, what this means is, since it is more linear as opposed to branching like butanoate, it's going to have a higher molar entropy in comparison to butanoate. And then when we compare ethyl vinyl ether to our final molecule, it doesn't have a ring, but it's also branched and it has a double bond, and that's going to limit some of the flexibility compared to the more extended structure in ethyl vinyl ether. So overall, this is going to be the molecule with the highest molar entropy because it's the floppiest, least branched, and most flexible of the four. So 30 is C. Problem 31 says, how many of the following processes increase in entropy? Let's go through each option. In process 1, we see methane gas turning into methane liquid. This is a phase change from gas to liquid. Since gases are more disordered and they have higher entropy than liquids, going from gas to liquid means that entropy decreases. So this does not count as an increase in entropy. Then we can look at process 2. Here we're going from 4 moles of gas to 2 moles of gas. So the number of gas molecules decreases. That's going to result in lower entropy. So again, this is a decrease in entropy. And then looking at our third process, again, we go from 7 moles of gas to just 6 moles. So this decrease in gas molecules leads to a decrease in entropy. So in all three processes, entropy decreases, not increases. That means the number of processes that increase in entropy is 0, and the correct answer is A. Problem 32 says a mole of liquid in a lab evaporates at 127 degrees Celsius, absorbing 100 joules of heat. What is the change in entropy of the surroundings? So the key formula that we're going to use here is that the entropy change of the surroundings equals the negative of the enthalpy change of the system divided by temperature in Kelvin. We're told that the enthalpy change of the system, which is the heat absorbed during evaporation, is positive 100 joules per mole. Since the liquid is absorbing heat from the surroundings, that heat is leaving the surroundings, which is why we take the negative of the enthalpy value in this formula. Next, we need to convert the temperature from degrees Celsius to Kelvin. The temperature is given as 127 degrees Celsius. This is equal to 400 Kelvin. Now we can plug in these values into our equation. The entropy change of the surroundings is equal to negative 100 joules per mole divided by 400 Kelvin, which gives us negative 0.25 joules per mole per Kelvin. The correct answer here is D. Let's move on to our next problem. This one wants us to calculate delta G of the reaction for the following at 200 Kelvin. To calculate the standard Gibbs free energy change for this reaction at 200 Kelvin, we'll use the Gibbs free energy equation. The change in standard Gibbs free energy for the reaction equals the change in standard enthalpy of the reaction minus the temperature times the change in standard entropy of the reaction. But before we can plug anything in, we need to determine both the enthalpy change and the entropy change for the overall reaction. To do that, we'll use the standard enthalpies of formation and the molar entropies that are provided in this table. Let's begin with looking at the balanced reaction. We have 2 moles of potassium chlorate in solid form. It decomposes to form 2 moles of potassium chloride and 3 moles of oxygen gas. Let's start by calculating the change in standard enthalpy of the reaction using the enthalpies of formation. The formula is that the change in standard enthalpy of the reaction equals the sum of the standard enthalpies of formation of the products, each multiplied by its coefficient in the balanced equation, minus the sum of the standard enthalpies of formation of the reactants, again, each multiplied by its coefficients. So looking at the products first, we have 2 moles of potassium chloride. Its standard enthalpy of formation is negative 437 kilojoules per mole. So 2 times negative 437, that gives us negative 874 kilojoules. The other product is 3 moles of oxygen gas. Oxygen is in its elemental form, so the standard enthalpy of formation is 0. 3 times 0 is 0. So altogether, the total enthalpy contribution from the products is negative 874 kilojoules. Now for reactants, we have 2 moles of potassium chlorate, which has a standard enthalpy of formation of negative 391 kilojoules per mole. 2 times negative 391 gives us negative 782 kilojoules. So delta H equals the total for the products, which is negative 874, minus the total for the reactants, which is negative 782. That gets us negative 92 kilojoules for the enthalpy change of the reaction. Next, we calculate the change in standard entropy for the reaction. The formula is very similar to the one we used for enthalpy. The change in standard entropy of the reaction equals the sum of the standard molar entropies of the products, each multiplied by its number of moles, minus the sum of the standard molar entropies of the reactants, again, each multiplied by the number of moles. So on the product side, we have 2 moles of potassium chloride, solid, and the molar entropy of potassium chloride is 83 joules per mole. So we multiply that by 2. That's going to give us 166 joules per Kelvin. We then have 3 moles of oxygen gas with a standard molar entropy of 205 joules per mole. We multiply that by 3, that gives us 615 joules per Kelvin. Adding these together for the products, we get that the total entropy contribution is 781 joules per Kelvin. Then we subtract from that the entropy contribution of our reactant. We have for our reactants 2 moles of potassium chlorate solid, and its standard molar entropy is 143 joules per Kelvin. So we multiply that by 2 to get 286 joules per Kelvin. So delta S of the reaction is going to be 781 minus 286, which gives us 495 joules per mole per Kelvin. Because our enthalpy was in kilojoules, we're going to convert entropy into kilojoules by dividing by 1,000. That gives us 0.495 kilojoules per Kelvin. Now we can go back to our main equation and plug in the enthalpy and entropy values we just calculated. So delta G is going to equal negative 92 kilojoules per mole minus 200 multiplied by 0.495 kilojoules per mole per Kelvin. And that will give us a delta G that is equal to negative 191 kilojoules per mole. So the correct answer for problem 33 is C. Problem 34 says zinc can be dissolved in hydrochloric acid following this chemical equation. The reaction is especially dangerous as the heat generated by the reaction can ignite the hydrogen gas, causing a fire. What are the signs of delta S, delta H, and delta G for this reaction? Let's begin by considering the sign of the enthalpy change, delta H. The question mentions that the reaction is especially dangerous because it produces enough heat to potentially ignite the hydrogen gas. That tells us that the reaction releases energy as heat, which makes it an exothermic reaction. And because it's exothermic, the enthalpy change is negative. Next, we think about the sign of the entropy change, delta S. Entropy reflects the disorder or randomness of a system. On the left side of the reaction, we have a solid metal and an aqueous acid solution. On the right side, we still have an aqueous solution, but now we've produced a gas, which has much higher entropy. So we're gaining a gas molecule in the system that increases molecular randomness, meaning the entropy change is positive. Now let's figure out the sign of Gibbs free energy change, or delta G. This value is going to tell us whether the reaction is spontaneous or not. Since we've determined that the enthalpy change is negative and the entropy change is positive, looking at our table, this guarantees that delta G will be spontaneous at all temperatures. So that means delta G will be negative at all temperatures. To summarize, the entropy change is positive, the enthalpy change is negative, and the Gibbs free energy change is also negative. So the correct answer here is D. Problem 35 says, when will the following process occur? We go from liquid ammonia to gaseous ammonia. So with that in mind, let's think about the entropy change first. We're going from a liquid to a gas. And when a substance goes from a liquid to a gas, the molecules move further apart and they become more disordered. Gases are much more disordered than liquids, so that transition results in an increase in entropy. That means delta S is positive. Now let's consider the enthalpy change, delta H. Vaporization, going from liquid to gas, it always requires energy to break the intermolecular forces that hold the liquid together. So this is an endothermic process. Because energy is absorbed, the enthalpy change is positive. Next, we're going to use these two facts to figure out the relationship between Gibbs free energy, enthalpy, and entropy. We know that delta G is equal to delta H minus T delta S. Since entropy and enthalpy are both positive, the reaction will be spontaneous at high temperature, which means delta G will be negative at high temperature. So 35 is C. Problem 36 says a reaction has these thermodynamic values. Delta H is equal to negative 400 kilojoules per mole. Delta S is equal to negative 10 kilojoules per mole. At what temperature does the process change from spontaneous to non-spontaneous? Is the process spontaneous above or below this temperature? To figure this out, we're going to start with the equation that relates these values, the Gibbs free energy equation. It states that the change in free energy, delta G, is equal to the change in enthalpy minus the temperature times the change in entropy. Now the reaction, it becomes non-spontaneous exactly when delta G is equal to 0. That's the transition point between spontaneous and non-spontaneous behavior. So we set delta G equal to 0, and we solve the equation for temperature. That gives us the following equation. Temperature equals delta H divided by delta S. Now we can plug in the values. The enthalpy change is negative 400 kilojoules per mole, and the entropy change is negative 10 kilojoules per mole per Kelvin. So we get that T is equal to 40 Kelvin. That tells us that the reaction becomes non-spontaneous at 40 Kelvin. So we have to ask a follow-up question. Is the reaction spontaneous above this temperature or below it? To answer this, we need to think about the signs of delta H and delta S. In this case, both are negative. That means that the reaction is exothermic, it releases heat, and it also results in a decrease in entropy. Now, when both delta H and delta S are negative, the spontaneity depends on the temperature. Specifically, at low temperatures, the negative enthalpy dominates, making delta G negative, and the reaction spontaneous. But at higher temperatures, the T delta S term becomes large enough to overcome the negative enthalpy, and then delta G becomes positive. That means that the reaction stops being spontaneous in that case. So we conclude the reaction is spontaneous below 40 Kelvin and non-spontaneous above that temperature. So the correct answer here is D. On to our last and final problem. This one says, which compound is the most stable? To answer this, we just need to remember the meaning of the standard Gibbs free energy of formation. This is the change in free energy when 1 mole of a compound is formed from its elements in their standard states under standard conditions. A more negative value for standard Gibbs free energy of formation means that the formation of the compound is more thermodynamically favorable, and therefore the compound is more stable. So we're looking for the most negative value because that corresponds to the greatest thermodynamic stability. The compound with the most negative standard free energy of formation is calcium carbide, and it has a delta GF that's equal to negative 65 kilojoules per mole. So 37 is B. And with that, we've completed this practice problem set. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.